Well, hi everyone. Good morning or good afternoon, depending on where you are, and welcome to this month's SLCAN webinar series. We're very pleased today to have Doug Ross with us to give us a total system approach to designing economically viable and sustainable exhaust systems for critical environment applications. Doug has presented with us before, but for those of you who didn't participate in that last webinar, I'll just give you a little bit of a background on Doug. Doug's an instrumentation and control engineer from the Auckland Technical Institute in New Zealand. His expertise was quickly recognized. He successfully completed turnkey automation projects for companies like Ford Motor Company, Fisher & Paykel Healthcare, BHP, New Zealand Steel. Doug and his family immigrated to Canada in 2000, where he worked in the automation field in Canada on projects with Alcan, Chrysler, ABB. In 2013, Doug joined MK Plastics as the Canadian sales manager, working with Canadian sales reps with commercial, institutional, infrastructural applications where corrosive elements are present. Doug has worked on laboratory exhaust system designs both in Canada and Australia. Doug has a particular interest in the total system approach to designing economically viable and sustainable exhaust systems for critical environment applications, a topic he will be speaking on shortly. So without further ado, I will introduce Doug. I would ask that if anyone has any questions, you please type them into the chat box or the questions box at on the dialogue for the GoToWebinar screen, and we will certainly cover them off at the end. And without further ado, I'll introduce Doug. I'll turn it over to you. Thanks, Doug.
Thank you very much, Martin, and good morning or good afternoon to people who are on this webinar. So this is a PowerPoint presentation on, oh, you're going to hold up on me again. Oh, I've sat still too long, Martin. It's locked up on me again.
Okay, just having a couple technical issues here.
Not quite sure why. Okay, just hold on. Okay. Okay, must have sat too long. Okay, so the intent of this presentation is to help us with the understanding of the importance of turn-down range, which I'll explain what turn-down is, to identify techniques to optimize fan equipment selection, and also to identify control sequence design approaches to properly manage and report the critical parameters of the exhaust fans. As we understand, lab exhaust fans are a high energy user. Part of that is because they run 24/7. The other thing to understand is that the energy that goes into the lab, or the exhaust from the lab, cannot be recirculated, or the air cannot be recirculated about. So in a laboratory situation, 64% of the heating, cooling and ventilation energy is spent in doing that application. So it is very intensive, and we need to understand how to select a fan that is going to be able to do this, and work our way through the process to ensure that we are able to provide for the critical environment and in a safe and workable procedure, but also with the ability to make sure that we are being conserving of energy and understanding of the requirements. So the first definition I want to define is turn down. So turn down is the ability to reduce the airflow through the fan without opening up the bypass damper. If you open up the bypass damper, what you're doing is basically adding in more air to the fan so that it can maintain either nozzle velocity or without going into a cavitation operation, be able to maintain the static pressure inside the laboratory. So turn down is an important point and something that we'll be talking about, but please understand it is the difference between the maximum exhaust flow and the minimum operating conditions that we're looking to run the lab in. The second thing to understand is that lab systems today, as per ASHRAE, are normally designed as VAV exhaust systems. So this is a variable air volume system where you are taking air, in some cases, from the lab area, as well as the fume hoods, back through the lab exhaust fans. So now we have to balance the pressure requirements and the air change requirements of the lab area, as well as the pressure control on the lab control valves, which are these units at the bottom here, to ensure that we're getting the face velocity across the fume hood as required. So this being understood, a typical VAV system for a building consists of maybe 3 variables. In some cases, it will be for sure the number of air changes based on the area of the room, as well as temperature. And in some cases, depending on the operation of the area, you may want to know the occupancy of that area for various reasons. When you're talking about labs, unfortunately, it's not so clear. There are many variables that come into it. As you can see by this list of considerations, not all fume hoods are going to be running at the same time. Not all, some might be delinquent. It could be difference in time of day. It could be the difference between the sash position of the fume hood. Therefore, the face velocity or the volume of air is going to differ. All these things need to be taken into consideration and thought about. So your VAV control system now has to be a little bit more complex than just a straight timing or function of air changes and temperature. So with that in mind, let's talk about how we're going to control these points. So most fans, lab exhaust fans, are driven by what is called a constant duct pressure, which is a pressure transducer that is placed on the exhaust plenum, which is, as you see by the pointer here, the plenum where the fans are attached to. So we are picking a pressure here, inches of water gauge, that is going to ensure that the fume hood at the furthest point is achieving its 100 feet per minute face velocity by controlling the lab control valve here or providing enough air through the lab control valve to do that without it going into alarm. This is normally a very broad brush approach, and so it is quite coarse in its control. So all we're doing is we're taking a pressure, we're saying it's 5 or 6 inches of static pressure, and we are guessing that everything's working because we're not getting any alarms on our fume hoods. If you want to refine that a little bit further, we can put a pressure transducer onto the 1/3, 2/3 track, which is called a variable duct pressure. We're getting a little bit closer down into the lab control valves above the fume hoods, and we're getting a little bit more precise in our pressure setting, but still we're still taking an average or a guess at the furthest point from that. If we were to take dynamic duct pressure, which is duct pressure reading from the lab control valve itself from the furthest point, now we're actually getting a very good control point because we are only providing enough static pressure, which is the work that these fans have to do to ensure that the fume hoods are working at their optimum operation. So let's have a look at how this works. We're going to take some assumptions in my discussion here. The first thing is that ANSI Z 9.5 is a recommendation for designing critical exhausts, which talks about requiring 3,000. If you're not doing a wind wake analysis, then you can rely on ensuring you get 3,000 feet per minute minimum discharge velocity from your nozzle, and that discharge point is 10 feet above the deck of which the fan is mounted on. And from a control perspective, all these fans will be controlled with VFDs. So whether they're belt drive or direct drive, the VFD is what is going to give us the ability to control them. So let's have a look at scenario number one. Scenario number one is a constant control duct pressure, so that the pressure transducer is in the plenum. It's an N+1 configuration, so there are 3 fans total, 2 running and 1 standby. And I'm going to be running a system that's about 100,000 CFM at about 4.5 inches of static pressure, which is a fairly typical larger requirement. Normally 4.5 inches could be because of a heat recovery coil, a runaround coil that's inside the plenum, giving us that additional static pressure. Or it could be a very large building. Let's have a look at what our selection is. So we're keeping in mind that the whole idea of what we're trying to do here is understand energy costs. And we want to use the bypass damper as minimally as possible. Like I said, for the turn down is really only effective if you can turn it down without opening the bypass damper. So in my first example, I have a 54-inch fan that I'm running 2 of them at just short of 50,000 CFM each. They are operating at 4.5 inches of static, as you see here, and my nozzle velocity is over 6,000 feet per minute. You can see that I am in a good operating position on the fan curve. And for those people who don't understand, the FEG rating that you see on the side here, FEG 90, is a fan efficiency grade. That is purely a measurement of the energy put in to generate the volume of air passed by the fan, irrespective of belt drives or any other losses that go into it. It's a test that's done by AMCO using a dynamometer. And FEG 90 is the highest grade of fan that you can get. So previously I used to have to show lots of tables, but now I don't, because the FEG grade tells us that it is a very efficient fan. You can see that my total efficiency here is at 80% and my static efficiency is nearly at 60. So I have a very efficient fan that's working, and on an energy cost of 10 cent kilowatt hour, we are consuming, if this was to run 24/7 at that rate fully all the time, it would cost us $80,942 a year to run. Now, you could say, well, that's running at 6,000 feet per minute nozzle velocity and you only need 3,000 feet per minute. And that's true, but the reason I show it this way is because there are fan manufacturers out there or engineers out there who select a fan at 3,000 feet per minute nozzle velocity at the design stage. When you're at the design stage, you are required to design it at full volume. So if your full volume is at 3,000 feet per minute, as you go through your turn down, you are going to have to open up your bypass damper. Effectively, you are going to be running this at its full capacity for the 24/7, even though you're turning it down. So this is part of where we need to have a look at the energy costs and what's involved here. So this $80,942 is a true cost for a 24/7 fan working at a energy cost of 10 cent kilowatt hours. Now, some people are less than that, some people are more, so you can do the maths accordingly. So now let's have a look at what's going on. Let's add some control to the system. And by adding control, we're going to decide that really we don't need to run it at 24/7 at that full volume, because for a portion of the day at night, there is not so many people in the lab, or the lab is actually not being used at all. So I'm going to say that for 50% of the time, I'm going to turn it down to a 60% turn down, which is going to be somewhere around about 70,000 CFM between the 2 fans. Still maintaining the nozzle velocity of 3,000 feet per minute or greater, okay? So if I'm going to do that, you're going to see this is a double fan curve. So this is at its lower volume. You can see it's still in the good part of the fan curve, as well as in the 60,000 feet per minute band. It is also in the good part. So we don't have any worries about stalling the fan by slowing it down. We have dropped our nozzle velocity down to just over 4,300 feet per minute. But the important thing here is that our brake horsepower has dropped to 18.5. So we've dropped it from 62 down to 18. This is a huge saving in power. How much is it saving in power? It's going to save somewhere in the vicinity of $28,000 per annum. And all I've done is taken in one change in my timing. So I've saved 50% not quite 50%. I've saved $28,000 per annum of my energy costs, just by putting in a control mechanism that allows me to turn down this fan without opening up the bypass damper to achieve that energy saving. Now let's talk about it really, because if you follow the ASHRAE documents, ASHRAE gives you a guideline of the use of a fan, of the exhaust fans of the labs through the day. And you'll find that really the total volume really is only used, I'm going to say 5% of the time for the purpose of this presentation. But in reality, the full volume is only used maybe at startup, and sometimes if there's been a spillage, or depending if there is a smoke and fire or emergency component to your control, that you need to evacuate the air in a short period of time. So 5% of the time, I'm going to say that it's for this purpose, for our model, I'm going to say we're running at the 100,000, just short of 100,000 CFM. 65% of the time, I'm going to say we're running at the slightly less, at 60% of the volume, or 40% down. And then at 30% of the time, I'm going to say we're running at 50% of the volume, which would be all your nighttime and weekend, public holidays, those types of times for the lab. So if we put that into the selection, we now find that we've dropped from 66 or 60, just over 66 brake horsepower for full volume, down to 18 for a 40% turn down to 6.21 for our lowest volume for what we're now calling the night mode. You'll notice that I'm still doing the 3,000 feet per minute nozzle velocity, so I'm meeting the ASHRAE requirement. Now, if your design was that the 3,000 feet per minute was not there, and you needed to meet a plume height because of the requirement for the job, then you would have to add in some bypass air to give you that plume height, because you've got to get the air from somewhere, and that would increase your brake horsepower. But what I'd ask you to do as engineers is go back to your wind wake analysis people, or whoever's asking you for that plume height, and ask them if there's a dilution factor in that calculation, because these are high plume induced flow fans, which means they induce fresh air through the wind band and through the center of the nozzle in this particular case, and they dilute that exhaust air by up to 170% of its volume. So you may not need to have the same plume height in the middle of the night when the contents of the air does not have the same contaminants in it that it would have maybe when the lab was in full use. The other thing I'll draw your attention to is I have here exhaust momentum. And part of why I put this here is because with plume height, there are two ASHRAE calculations. In fact, there's three, but the two I'm going to talk about are 2007 and 2011. And of those, there are 13 variations inside that calculation. So depending on how somebody calculates their plume height, they can make a plume height be of a certain height by that calculation. That doesn't mean it's necessarily going to mean that it's going to meet it in your application. And the only test and balance work that is done inside the building. So you need to protect yourself as engineers from this by saying, well, how do I check that if manufacturer A is telling me his plume height is 44 feet and manufacturer B is telling us that it's only 30 feet, how do I know which one is right? So it's a very simple calculation. You take the CFM, which is the number that the engineer, it is what you've calculated, so that will be true to you. And then you take the nozzle velocity, which is part of an AMCA certified fan test for the 260 AMCA certification, and you multiply those two numbers together. And as you'll see, you'll get a very large number. And all you need to do is to say, is to look at that, and if somebody's saying that they can get 44 feet with their fan and the other person is only getting 30 feet, you just need to look at which is the larger number. And that larger number will tell you, well, hold on, I need to get more clarification on this, because if this one is larger, is it correct? Who's telling me the truth? So I put this in here for a verification of momentum, because the last place that we can add energy to this exhaust air is at that nozzle. Okay. Once again, you'll see that my system bypass is 0, so I'm not putting any bypass air in here at all, but I have reduced my fan brake horsepower, the energy consumption, quite considerably. So you can see here that I've saved by variable duct pressure, by putting my transducer at the 1/3, 2/3 position, and by putting in the time differential, I am able to now reduce my total consumption of energy by a further $30,000 or $31,000 per annum. This is quite a substantial saving. So I have one last step that I want to talk about, and this is an alternative system design. So we've been speaking about a system design that is N+1, which is a redundant fan, and this is all well and good. The redundant fan works very well. It's a well-tried system. You have a control system that rotates that fan so that it doesn't sit idle for too long. Therefore, there's no damage done to the bearings or the operation. You know it's going to operate because it operated last time, so it should operate again this time when it is put on. And so you have a number of fans plus one redundant that you operate around. An N-1 system is a system where instead of having the fan sitting redundant, what you do is you have the fans running so all fans meet the total flow of the system, and should one fan fail, then the remaining fans will now step up to increase their volume of flow to meet the requirement of the total flow. So this can be a very advantageous design when you're looking at a BSL 3 or greater lab, because once you start getting into those higher usage labs of more critical environments, the allowable drop in static pressure should a fan fail before the system has to ramp up to full volume is 10 seconds. So that 10 seconds to go from 0 to 100% is not very long, but 10 seconds if you're already at, say, 60% to go up to 100%, now you're going to maintain your static pressure inside that 10 seconds and you will have better control. This scenario that I'm about to run also looks at the dynamic pressure control, which is the pressure control at the lab valve itself. This can be done either by taking the furthest lab valve from the system and taking the pressure reading from that, either via BACnet or through a control of analog control of 4 to 20 or 5 to 10 milliamps, depending on how your controls people want to run it, and feeding that back, cross-referencing it with a 1/3, 2/3 pressure transducer so that we don't try and get the fans to operate at the change of a sash position or of a sudden change with one fume hood, because that will cause hunting and a very unstable fan operation. So what we want to do is to have a control system that is able to read the furthest control and compare it with the basis of where we stand for turning the fans on and off, and where that will lead us. So in this scenario, I'm going to be using the same time distribution and turn down volume conditions as we had in the previous scenario 2, but I'm also going to have 3 fans operating with the capability to ramp up the remaining 2 to full flow on demand, so if one should fail. So this is what we call an N-1 configuration, and we've used it in quite a number of applications. What I would like to interject here with is that the California Title 24 standard is calling for either a air quality check and or a weather manometer to be included in the control system of the exhaust fans, lab exhaust fans, to ensure that we have a reduced energy cost. This is quite possible. It will have some effect, and I've put it in here because we're able to do it both ways. With a wind manometer, you can, if the wind direction changes from the south to the southwest and it picks up that it could be of a velocity that it could cause re-entrainment of the exhaust into a building somewhere, then the control system will call for that nozzle velocity or the plume height to be altered to ensure that that doesn't happen. That control will be a secondary control. You can't add, I can't just add nozzle velocity and add air by taking it out of the laboratories or out of the fume hoods, because that would change the operation of the fume hood. So I need to take it from somewhere else. I will take that from the bypass damper and therefore ramp up my brake horsepower to account for it. So the same thing will be with the monitor for the air quality of the lab. In other words, the contaminants that are in the exhaust duct. If the contaminants are noted to be high, then we will turn on maybe more fans or increase the volume of the fans to remove it. And if it's the air changes, or sorry, and if the contaminants in the duct are less, then I will turn the unit down accordingly. Obviously, at some point, we can only turn it down so far. So if the number of air changes goes down to a number where the exhaust fans are not meeting the 100 feet per minute face velocity, then we need to increase the static pressure or change the air accordingly going through the fans. Therefore, the brake horsepower will change. The comment about emergency conditions you see here on the slide, the emergency conditions could be a spillage, therefore the contaminants would be very high and they need to be removed from the air very quickly. So therefore I might need to turn on more or a higher volume of air, or it could be that you are using them also for smoke removal, and that would also require to increase the flow. The important thing here is that static pressure of the system is always going to be our number one measure. That is what we're there to maintain. If we don't maintain static pressure, the operation of the lab, the fume hoods, is not going to be as effective as they should be. So static pressure is our primary control. These other things are secondary, and they would be taken into consideration and operation accordingly because of it. So it would be a secondary stage, and it needs to be understood by the control person as to how to put these things in so that they don't cause hunting or irregular or erratic operation of the fans, and therefore shorten the life of the fans themselves. So let's have a look at where we're at for the fan itself in scenario number 3. This is an N-1 configuration, so I've got 3 fans running. As you can see here, 3 fans are operating throughout the system. And I have my volume of air. Now, because I am running 3 fans, my volume of air for all 3 to meet the 100,000 CFM or close to it is less. You might notice, if you were observant, that my model number has changed. So I've gone from a 54-inch fan to a 49-inch fan. That means that my cost to install this is reduced, but also my footprint. So sometimes it could be a good idea to think about footprint requirements and to look at maybe looking at an N-1 type application might be a solution for you. My brake horsepower here, my horsepower of my motor has stayed the same, but my brake horsepower is greater at the lower areas, but far less at the top level. So we're still maintaining a good nozzle velocity, and my exhaust momentum is consistently high. You'll notice that it changes in the middle with the fans. That's because of the volume of air and the nozzle velocity, the speed of the unit. But I'm still not using any bypass air in this system. So what does this look like as an energy model? So here you can see that my energy really is a little bit higher. My energy cost, it's just over the 20 or just over $25,500 in energy costs. But remember that my initial cost and my area for the unit is down. So my total project savings on this is about $5,000 in the overall design of it. So while I haven't got the most economical energy model, having maybe saved some money on the initial design will allow it to be more acceptable to my client. So what does this mean in general? So basically what it's telling us is that the total energy savings achievable in the an M+1 system is just shy of $60,000 per annum if I take into account the position of my transducer, my pressure transducer. So I have a variable duct transducer that is in the 1/3, 2/3 area of the main duct, and I am running a time shared or time controlled operation. So in other words, I call it day-night, but it could be by, you could have occupational people. I know there's a number of fume hoods that have sensors in front of them, sensors that can tell if there's a person standing in front of them or not. You may want to have a head count in there. There's a number of things you could put in there to add to this control to make it more effective. And this is all assuming that also that the lab personnel are functioning in the lab as they should. So what they are doing is they are ensuring that all the contaminants are carefully stowed away, that the stoppers are in them, that the sashes are in the right position for their operation. Everything is in that respect is under control. The total energy savings for the N-1 system is just over $50,000 per annum, plus the initial cost savings on the unit. So if you add that in, the difference between the N-1 design and the N+1 design in this system is about probably $2,000 difference in overall energy cost. Now this is per annum, so the life of these fans is somewhere between 10 and 15 years. So you're going to be looking at a considerable savings over the life of the fan, and therefore your return on investment for your end client, they will pay handsomely for these fans and the operation over that time. And so they have payback over that time. So what are we saying here in summary? What we're talking about really is with when selecting your high plume dilution fan, ensuring your nozzle velocity is sufficient to allow substantial turn down. So you want to have a turn down at least 40% turn down, if not 50%, without opening up the bypass damper. That will give you the ability to save the energy that we're talking about. Added to that, you also need to think about where the pressure transducer is going to be placed and how you're going to put in your controls for that, for making sure that you're able to get the optimum operating pressures that are required, as opposed to a general operating pressure. So if it's in the plenum, it's a very general operating pressure. I'm saying it's 4.5 inches of static. I could be seeing 2.5 inches at the furthest point. I'm not getting an alarm on my fume hood cabinet, so everything's working fine, and my face velocity's been tested and it's well within 100 feet per minute, so I'm okay. But you could be spending a lot of money on energy that is not necessary. So for a little bit extra care and a little bit extra cost, you can save a lot of money. The other scenario is that you need to look at is more than just selecting a fan. So this isn't just selecting a fan with the CFM and the static pressure. Here we're looking at what is the area it's got to go into, what is the function of this, what's my primary area. Am I more concerned about plume height, or am I more concerned about energy? Am I more concerned about what my static pressure needs to be? What are these things that we're looking at? And once we've defined that, then we can go further and define which fans are going to best be suited and in which arrangement are we going to be best suited for your application. So hopefully, based on this information, as you go through your fan selections for laboratories, it will make you think a little bit more about how you're using them, what you're using them for, and what are the criteria that we have to try and meet to get this fan to work correctly. And with that, I would say thank you. And if you have any questions, I'll be happy to take them.
Great. Thanks very much, Doug. I'll give people a few minutes to type in any questions they may have, but there is one already. You talked about over the life cycle of the 10-year life cycle of the exhaust fan. Mm-hmm. Are you saying the N+1 or the N-1 is a more efficient?
That's a good question. So it is probably project specific, because an N-1 application in a 2-fan application, like, so you have one fan running and one fan redundant, or you have 2 fans running, the size of the fan is going to be the same fan. When I have to, if one should fail and I have to step it up to meet it, it's going to be the same fan. So an N-1 application in that would not be efficient. Where you have maybe 3 or 4 fans in an N+1 arrangement, and sort of somewhere over the, I would say 60 or 70,000 CFM range, now the N-1 becomes a viable option to look at, because you are potentially going to save on your initial cost, and you're not going to, depending on the volume and what your criteria are, if it's 3,000 feet per minute nozzle velocity or if it's a plume height requirement, you are not going to see the same sort of energy savings, but you will make it up with, on an N-1 arrangement, you will make it up with the initial cost of the purchase of the units will be the difference. So the savings will be there, but it depends on the type of project.
I guess on the footprint as well.
Yeah.
Yeah. Okay. I'll give everybody another minute or two to put any more questions, and we'll see what we got here. You've provided some very interesting energy cost comparisons that owners can take advantage of. Do you have any experience with systems like Aircuity, which samples the contamination in the plenum of the exhaust and can reduce the exit velocity with the aim of saving energy usage?
To answer your question, yes, I do. I have had Aircuity systems run with our fans and our control systems. The important thing you have to understand when you're looking at something like an Aircuity system, which is working on measuring the number of air changes or the contaminants that are in the airstream, is that if the fan is not selected correctly and you have to open up your bypass damper, or in some cases, some fan manufacturers actually use bypass air constantly to provide the volume for their nozzle velocity, then your energy savings are going to be attributed accordingly. So the more you have to open up your bypass damper to accommodate what the Aircuity system is asking the fans to do, your energy saving is going to be reduced. So my experience with Aircuity is that it works very well with fans that have the ability to turn down their to have a turn down range somewhere in the 50% range, because that tends to be where you're at. I believe that Aircuity can turn down the air changes of a laboratory from anywhere from 8 to 12 down to something like 2 to 4. But there's probably people with more experience in Aircuity than me that can answer that question.
Okay. Another question. Doug, thanks for your presentation. Do you still see many constant volume applications versus VAV?
So I do see a number of constant volume, but they are being reduced since the ASHRAE 90.1 is basically encouraging or asking or stipulating people to go to VAV controls. And as the air changes from the laboratory area are now being combined with the exhaust fans, the VAV controls is becoming more and more integrated with the lab exhausts. So while I am seeing some constant volume, I would say it's in the lower numbers compared to the VAV.
Okay. Another question here. Is the payback period for adding the additional control features needed for VAV attractive for the owner-operator versus constant volume operation?
Yes, they are. If you're talking about something like a wet lab in a K-12 school, then obviously having a constant volume is really all you need, because you can have it switched on or off or running for the 1 or 2 fume hoods that they are running in that scenario. But if you start talking about a development lab where you've got a number of fume hoods, or in a university where you've got a number of fume hoods running, the control side of it is not a high percentage of the cost of the system, and comparing that to the energy savings, as you just saw in my presentation, I mean, we're saving nearly between $50,000 and $60,000 a year in energy savings. There's no way that the cost of the controls is costing you that, even in the first year.
Okay. Another question. Have you installed as a retrofit, for example, in existing lab buildings from the 60s, 70s, and 80s, this type of full system upgrade? If so, are there any lessons learned that you can share? Logistically, what did you find was the biggest challenge?
That's a good question. I can't think off the top of my head of a system where I've done a retrofit. We have replaced fans, but in replacing fans, we're putting in the whole system. So we have control over what's going on. I guess the biggest problem with retrofits into an existing building is the running of control feedback. If we're going to the dynamic control system, running it from the furthest unit back is from the furthest unit away, furthest fume hood away from the fan, then the control wiring would be an issue. I would have to talk with the engineer and find out how easily or how difficult that was, and whether it would be viable to do. But in general, the changeover from a retrofit from an older building to new, we tend to be putting in things like heat recovery as well as the fans, and there are other considerations to be made with that. So it's normally a whole system that we put in.
Okay. Okay, well, I don't see any other questions, so I guess we'll let you go then, Doug. On behalf of Sustainable Labs Canada, I again thank you for your time today and for your presentation. I think everyone enjoyed it. Judging by the number of questions we had today, I think you very much enhanced the knowledge of exhaust fans. So on behalf of SLCan, thank you.
Thank you for everybody for giving me some time, and thank you, Martin, for setting this up, and SLCan.
Great. Okay. Take care, everyone. Bye now.
Thank you. Bye now.